He was really terrific. Our book actually has solving a nice treatise to solving the wave equation using separation of variables, and Chris Tisdale, he goes through it so slowly. It really is nice. So I thought what I'd do is work through just what you were asking with real numbers and real functions, and I think at some time I put an actual initial condition in there, but I wanted to walk through what it looks like with an actual number in there. And there's a picture, a sample picture of my waving guitar string. So, and there's my u of xt, which is the displacement and the location, and we just talked about the derivation. And what that means is the ends are clamped, just like in the guitar string. What does this represent right here? I gotta move, I feel chained. So this represents the initial displacement. So whatever, it might be, there's a picture in Mike's book where you're just pulling the string and you see that tent. So that might be the initial displacement. You can think of, I'm going to pull this guitar string and then let it go. So that's the initial condition right here. And the ut being 0 at time equals 0 just means that you pluck it, you're holding it, and you let it go from rest. So imagine that the string is being plucked. This is state 0, it looks like a tent, and then let go. So let's put a real initial condition on there too, so we can see the whole dirty details mapped out. The one that I drew here is the tent. And if it wasn't a tent, if it was a curve, I would approximate it with a tent. So, first step is like we always did. We assume that the solution is of the form x of t times t of t, u of xt. If you're taking notes, maybe I'll just slow down and let you take notes. Just tell me and I'll slow it down. Then you substitute this into the equation. So you're going to get utt is x times t double prime. Uxx is x double prime times t. And then when you put it into the equation, you get the same separation of variables formula that we've gotten before. And when you cross multiply, you get the fact that you have all the x material on one side and you get all the t material on the other, and the only way a function of x could be equal to a function of t is if it's constant. So we set it equal to a constant, and this time I set it equal to mu because I know the lambdas are going to come. So write down the equations. These are my two sets of equations. They look a little bit different because one of them is not first order as it was before for the heat equation. And the goal is to find the values of mu that yield non-trivial solutions. So step 2 is to find the characteristic equation of one of the equations. So I took the first one we have listed, x double prime equals mu x. And we find the characteristic equation. It's the characteristic polynomial. It is exactly the characteristic polynomial from linear algebra. It's the same thing. So you take, the way you do this in a slick way without matrices is you let x equal 1, x prime equals lambda, and x double prime equals lambda squared. But we don't have an x prime, so we don't have to worry about it. So we get lambda squared minus mu is equal to 0, or lambda squared is equal to 0. So then you go through the cases. Mu is greater than 0, mu is less than 0, mu is equal to 0. As in the heat equation, two choices of mu are going to lead to trivial solutions, and that's going to be mu is equal to 0 and mu is greater than 0. So I'm going to skip those steps. We've seen them before. And we're going to try the case at mu less than 0. Mu less than 0 gives us that lambda squared is mu, and then when we take the square root, did I make a minus sign error here? We get lambda equals plus or minus square root of minus mu times I, because mu is less than 0. So you write out the general solution for x and apply the boundary conditions. That's the next step. So there's the general solution for x. It's a cosine square root of mu x plus b sine, and I guess I have my minus. You need the minus sign in there, right? So you have those in there. And I know that u of 0t is equal to 0 and u of pi t is equal to 0. So u of 0t, if I plug that in, I get x at 0, 0 because we don't want t of t to be identically 0. Likewise, if I plug in pi, I get x at pi is 0, and then x at 0 is going to be, oh, so now I can just plug in the boundary conditions. X at 0 being 0 implies that a is 0 by just plugging in x at 0 is 0. X at pi being 0 gives me mu is equal to minus n squared. So I really have bn sine nx, right? Because I'm going to have a bunch of solutions. So I have a sequence of solutions. So hold that thought. I'm going to move now to the second equation and do the same thing. But now I know the form of mu. Mu is equal to minus n squared. So I can plug in the value of mu, and I have this formula. So I get lambda squared is equal to minus n, 9n squared. I'm not going to go through the whole characteristic polynomial again. And then lambda is equal to plus or minus 3ni. So I can write down the general solution for t of t as well. And I don't have the cases here because I already know what mu is. And then we apply the principle of superposition. And this ought to be really pretty because we have a sum for a sequence for t of t, and we also have a sequence for x of x. And it is. Take a look at, feast your eyes on this. It's beautiful, isn't it? In which you can expand out. And what I did here is I looked at all the coefficients and I just glommed them into pieces. So I absorbed all the constants. So I have an a sub n and a b sub n. So far following? You get that. So I know that the problems that I gave you were tedious to run through, but when you run through a few of them, then you get the feeling for them, and it seems much more simple when you're seeing it again. So now it should look familiar. Now we're going to apply the initial condition. And here is the place where Sham's outline stopped you because you didn't have an actual function and couldn't crank out the coefficients. But this time we're actually going to be able to calculate the coefficients. This is the Fourier sine series expansion for the initial condition. So where this comes from, and what I'll do next week, I'll fill in some gaps. I'll go through Fourier series for you. The idea behind a Fourier series is that just like a Taylor series, you're taking a function and saying, I can expand this function in an infinite sum of polynomials. The same idea holds that you can take a function that's periodic and expand that as a sum of sines and cosines. And that's the concept behind it. Just like Taylor series, you have a formula for deriving the constants in terms of the derivatives of the function. Here, there's a formula for deriving the coefficients for that series that you're looking at. And this is the formula. There's an actual formula. And I haven't derived it, but next week I'll show you where that formula comes from. So that's the formula, and we know what the L is, the length of the string is. It's pi, so we can plug that in. And we actually know what the function phi is, so I can plug that in. And you actually have two integrals to calculate. If you remember in Calc 2, this happened when you had piecewise defined functions. You integrated up to where the function split in definition. You have one term like that, and then you have another term from pi over 2 on. Something like that ring a bell? This is on YouTube, so I'll announce the fact that most Calc 2 students just drive on with one integral and not split it up into two. But here you have, remember the tent. This is the first left side of the tent, and this is the right side of the tent. You have a different expression for both pieces. So this is the piece that's on the left side, and this is the piece on the right side. And in the case of Calc 2, you leave off the parentheses, as I did right here. So it's 2 over pi times the whole thing. So I just cranked it out on Maple. This is what you get. And you actually can crank out what it is. And I didn't make it look that nice. I just said zeros if n is even, and 1 if n is 1, 5, and 9, and minus 1 otherwise for the other odds. So the next step is to use that initial condition, plug it in. I know what the ANs are. Recall that the other initial condition was at the derivative, that we took that string in its initial position and then we let it go from rest. So the next initial condition, I needed to find the derivative of u first before I applied that second initial condition. And I do this by calculating the derivative term by term. So just take that expression for u of t and x, and take the derivative in time term by term, which gives me this nasty looking series here. But then I set that equal to 0. And that gives me that bn's are all 0. So now I have a formula for u of x and t. It's just the summation of n equals 0 to infinity of a n sine nx cosine 3n at t. I have something very specific. And I know what those a-n's look like, right? I already cranked that out. So I copied and pasted from a previous slide and put it up here. So I can actually write down the first few terms of this series. I just went ahead and plugged in. I plugged in n equals 0, n equals, I guess I did the first three non-zero terms, because a whole bunch of the terms rough out to be 0. So again, these are the first 3 non-zero terms of that series. And then I wanted to see what it looked like. That's what it looks like. So what are you looking at here? You're looking at, this represents the fretboard. And it's clamped at the ends. The string was plucked, and what you're looking over in this is an animation in time of the string waving back and forth over time. The vibrations. Or
the scale of t is from 0 to 0.40.
no, it's just got cut off. Yeah, it's
But after a certain amount of time,
I
it
agree.
actually winds up the opposite of where the initial.
right.
condition-
So there's some assumptions behind the model, right? That there's no resistance.
Yeah.
So there's nothing stopping this. It's just going to keep going back and up and down. So that's our assumption in play, that this is a wonderful perpetual motion that never stops.
And as you do more terms, it will look more like a triangular wave at the beginning, right?
Mm-hmm.
And this gives us it in general, so we can take a section of x and say this is our x and this is what it's going to look like.
Right, you're right. You can say, I'm going to still frame this at 1 second, and then this is what your configuration of your string is going to look like. So I called my kids over when I say, look, check this out. This is your guitar string.